So to find this height here, I'm going to label that height A. It's one we're normally given. Like I said, I did a poor job of drawing this. This should be symmetrical, and it's not, just because, well, I'm horrible with my artwork. But if we go from, the typical strategy here, connect the center of our circle down to the point of our V, that should be a vertical line. Then we connect over to the radii over to where the tangents are. Those are going to make right angles. And if I focus on this triangle right here, I know that this angle is 55 degrees. Where did I get 55 degrees from? Half of 110. Very good. This up here I know is 40 millimeters. It's just the radius of the circle. If that's 55 degrees and this is vertical, if I draw on a horizontal, what's this angle? 35, because that has to be a right angle. Vertical and horizontal have to form a right angle. So what that does is it allows me to come right here and make that triangle. And in that triangle, there's my 35-degree angle. So what I did there was I took a sloped surface and I made vertical and horizontal components of that sloped surface. This is the vertical component, this is the horizontal component of that sloped surface. Do I know any of the dimensions of that triangle other than the 35-degree angle? Well, no, we don't know them outright, but we can figure them out. We know if this is 200, if I subtract 50 and 60, this becomes 90, right? And again, we have to assume that V is symmetrical. That would make this 45, half of the 90. So that means I can find this here. I'm going to label that B. If I'm using my 35-degree angle, the 45 is which side of this triangle? That's the adjacent. B is the opposite. Opposite and adjacent make what trig function? There it is. Tangent of an angle is opposite over adjacent. So now we'll fill in what we know. Do we know the angle? Yes, it's 35 degrees. Do I know the opposite side? No, that's the B, what I'm trying to find. The adjacent side? Yeah, it's the 45. Am I looking for a side or am I looking for an angle? Looking for a side. When we're looking for a side, we put the trig function over 1 to make it a proportion. And we just cross, multiply, and divide. So this is going to be tangent of 35 times 45 divided by 1. I don't have to do the divided by 1 because that doesn't do anything. So 31.51. So B is 31.51 millimeters. So this dimension right here, 31.51 millimeters, which means A here is 68.49 millimeters. Where did I get the 68.49? Not from 90, but from 100, right? So that's that height from here to here. I know that from here to here is 40. All I need to find is this piece, which is the hypotenuse on this blue triangle. I have the 55. 40 is which side? Opposite. And of course, this is the hypotenuse that I'm looking for here. I'm going to call that C. What trig function deals with opposite and hypotenuse? Sine. Sine of an angle is opposite over hypotenuse. Do I know the angle? Yes, we do. So I'll throw in the 55 degrees. Do I know the opposite side? Yes, the 40. Do I know the hypotenuse? No, that's what I'm looking for. I am looking for a side again, so I put the trig function over 1 to make a proportion. Now here that 1 comes into play. It's 1 times 40, which is 40, divided by sine of 55. 48.83. So that's 48.83 right here. So we've got an overall height from the top of the round stock to the bottom of the block, which is going to be 40 plus 48.83 plus 68.49. $157.32 millimeters, correct? That's that dimension. Subtract the 100. You got it, 57.32 millimeters. But that's that round stock sticks out above there. What do you think? There's a lot of there's a triangle here, a triangle there. No. The nice thing about this is all flat. It's a flat cross section. So all these triangles are going in the same orientation. In about 3 weeks, we're going to hit three-dimensional shapes where you've got one triangle is going up and down, one triangle is going side to side, one triangle is going in and out of the paper. So you got right triangles connecting to each other in every different direction. So that's where the visual part of your brain has to do some overtime there to make that work. Okay, well, we're going to shift gears just a little bit. We're going to come back to these finding right triangles in these shapes a little bit more. We'll spend a couple weeks on them yet. But I want to look at what happens when we have a triangle that does not have right angles in it. That's called an oblique triangle. So it might be a triangle that looks something like this. Trying not to make that look like a right angle. So as we've been doing, we've got angles labeled A, B, and C. And the sides, side A is across from angle A. Side B is across from angle B. And side C is across from angle C. The sides are labeled by the angle that is across from them. Notice the angles are all capital letters, the sides are all small letters. We've discussed here before that the largest side is across from the largest angle. So let's label some angles here. What if I tell you that this here is 35 degrees, this here is 86 degrees. Of course, what does A have to be? Yeah, they have to add up to 180, so A is going to end up being 59 degrees. So those add up to 180. Which side has to be the longest side? C. Because it's across from the longest angle, or largest angle. Which side has to be the shortest side? B. Yeah, because it's across from the smallest angle. Well, that relationship is actually very specific and very useful. And I could derive it, but it would take us a long time. So this is one of the few times again where I'm just going to give you something and ask you to trust me that it's true. It's called the law of sines. And what the law of sines does is it's a way of quantifying this whole idea of the longest side being across from the largest angle, and the shortest side being across from the smallest angle. And the way the law of sines is written looks like this. In a triangle like we have here, angles A, B, and C, and opposite sides little a, little b, and little c. The ratio of the length of side A divided by the sine of its opposite angle is a constant for that triangle, within that triangle. So I can compare that to the length of side B divided by the sine of its opposite angle, angle B, which would also still be equal to the length of side C divided by the sine of its opposite angle, angle C. Now, to make this work, only works when you have a side and its opposite angle. In the triangle I have drawn here right now, I gave you all three angles, but I didn't give you any sides, did I? Wouldn't work really well in that triangle. In fact, I only gave you two angles, didn't I? I gave you these two, and we found the third one. So we're going to go case by case basis here with some examples. The simplest example we can use is if you're given two angles and one opposite side. We're going to see in a minute that it doesn't matter if that's an opposite side, but let's, for this example, we're going to use an opposite side. So let's say this angle here is 86 degrees. This angle here, we're going to put it 39 degrees. Now I'm going to put this side down here at 40 millimeters. Now that units of 40 millimeters on the 40 there really don't matter. All that means is all the other lengths are going to be in millimeters as well. So if I do some labeling here, I'll call that angle A, that'll be side A, this will be side B. Do I have a side and opposite angle? Yes, I do. Come on. Yes, I do. I have the 86 degrees and the 40 millimeters. So that means I can do this. I can do 40 over the sine of 86 degrees. Now, some textbooks do it as the sine of the angle over the length of the side. It's the same thing. It's just, for me, it's easier to the length of the side over the side of the angle. So now we have that number. Rather than calculating out what that value is, however, let's compare it to other parts of the triangle. Let's say I want to find side B. Well, B is a side, so does that go on top or bottom? Goes on top. What's its opposite angle? What angle is going to go down here? 39, so sine of 39 degrees. So right there, I can find the length of B. I'm going to cross multiply. 40 times the sine of 39 divided by the sine of 86. On your calculator with this one, you have to be very careful. So 40 times the sine of 39. Make sure that if your calculator uses parentheses, you close those parentheses. Don't have to put degrees. The calculator assumes the degrees. Divided by the sine of 86. I get 25.23 is the length of B. Yep. So we're calling it 25.23 millimeters. Now, since we were given two angles here, finding the third angle, in this case angle A, is pretty simple. It's what? How did I get 55 degrees? Yeah, we take 180 and we subtract the other two angles, we're left with 55 degrees. Once we have two angles, third one's always easy to find. So now that we have that angle, we can find side A. We start out with the same proportion, same ratio we had before. We still have the 40 millimeter side over the sine of its opposite angle, which is 86 degrees. Now looking for side A, it's going to be A over sine of 55. 55 is its opposite angle. So we're going to solve that. Again, 40 times the sine of 55 divided by the sine of 86. Making careful to close our parentheses. Yep, we're going 32.85, right? And there, we have found the missing parts. You bet. Now, over the next several days of class, we are going to discover that the only combination of three parts that does not work is if we're given all three sides or all three angles. As long as we are given at least one side, we can always find, if we have any three parts of a triangle, we can always find the other three parts. Here we were given two angles and one side. That always works. Two sides and one angle always works as well. All three sides works. It's just all three angles does not. Anybody tell me why all three angles wouldn't work? That'd be going back to what I gave you up here. If you had all three angles, if I could make a triangle that has those same angles, it's just smaller, right? Or just bigger or whatever. So having all three angles doesn't guarantee it's the same triangle. It guarantees it's similar. So that's case one, where we have two angles and a side that is the opposite side. Case two, we're given two angles and a side that is not opposite one of the angles between the two angles. So we might have this. Let's say we're given this angle here, 40 degrees. This one here will go 75 degrees. And the side in between them here, we're going to call 25 millimeters. So I've got angle C and I got sides little a and little b that are missing there. Do I have a side and an opposite angle? Do I have a side and an opposite angle? No. Can we find them? Well, yeah, because we can get this angle here really quickly. It is 65 degrees. Yeah, 180 minus 75 minus 40 gives us 65 degrees. Right? So once we find that third angle, now we have a side and an opposite angle. The side is the 25 millimeters over the sine of 65 degrees. Let's say we want to find side A first. What goes below it? Sine of what angle? 40 is the opposite angle. And we cross multiply and divide. 25 times sine of 40 divided by sine of 65. 25 times sine of 40. Again, be careful to close your parentheses if you need to. Divided by the sine of 65. 17.73. You guys come up with that? Sure. That's understandable. Perfect. Now to find the other side, we go back to that same ratio, 25 over the sine of 65. where we started here. We're looking for side B. It's going to go over the sine of 75 degrees is its opposite side. So we cross multiply and divide. 25 times sine of 75. Close the parentheses. Divided by sine of 65. We get 26.64. Now, as I look at these sides, one thing I can do to double check is, do these sides make sense? Which is my biggest side? 26.64, right? Is its opposite angle the biggest angle? Yes, it is. 75 is the biggest angle. My smallest side is the 17.73. Is it opposite the smallest angle? Yeah. So that doesn't guarantee they're right. It just means they make sense. It may stop us from making a really silly mistake. So anytime we're given two angles in one side, we can always use the law of sines. Always works. So let's move on to our other cases. Two sides and an angle. So if we're given two sides and one opposite angle, so let's say that's 80 degrees. We'll call this 90 millimeters. And we'll call this down here 75 millimeters. I'm going to label A, B, so we see a little a that's missing. Do I have a sine and opposite angle? Well, yeah, I said right there, given I'm going to give you an opposite angle. I do, and that's going to be which side? 90 over the sine of 80. Perfect. Now, I have, the only other piece of information I have in this problem is the 75 millimeters, isn't it? So I'm going to have to use that. That's the length of the side. It's going to go on top. Sine of what angle is going to go on bottom? What's the opposite angle from 75? B. So I'm going to find down here is angle B. Now notice what I'm finding is not B itself, it is the sine of B. Note that. So now we're going to cross multiply and divide. Now we're going to cross multiply this way. Sine of 80 times 75 divided by 90. Sine of 80 times 75 divided by 90. Gives us 0.8207. Now I'm going to leave that in my calculator. Notice it's not B equals 0.8207, it's sine of B equals 0.8207, which means B equals, we have to do the inverse sine to solve that, right? Of 0.8207. This is why I didn't clear my calculator. I'm just going to do inverse sine of that answer. Gives me 51.15 degrees. On your calculator, it's the second key. Then A on S, I believe, is your negative key down on bottom. 55.15 degrees, we'll call it. So B is 55.15 degrees. Now, so far we have tried to avoid using calculated values to calculate other values because of the round off errors. We can't avoid that anymore. We now have to find angle A here, and the only way to find angle A is 180 minus this angle minus one we just found, which is going to give us that's 44.86 degrees. And we're also going to have to use that angle to find side A. Now this is just like what we did in the last triangle. We still have the 90 over the sine of 80 degrees. We're still using that same first ratio. But on the other side, we're looking for side A, so that goes on top. And its opposite angle will be the 44.86. So it's over the sine of 44.86 degrees. And this is going to be a simple cross multiply and divide. 90 times the sine of 44.86 divided by sine of 80. Perfect. 64.3. Oh, I didn't get the 6 in there. Yeah, what, 46? 64.46. Yeah, I got 3.9, but I didn't get the 6 in there. 0.86, I got just 0.8. So 64.46 millimeters is that length. Not so bad, right? Well, there's two other cases we need to discuss. The first one, we're given two sides and the what's called the included angle. I'm going to say one angle between them. What does that mean? Well, let's say that this here is 75 degrees. And I give you that this side here is 30 millimeters and this one here is 50 millimeters. Do I have a side and opposite angle? Say no. Is there any way I can find a side and opposite angle here? Not from basic functions and law of sines. This one, we cannot use law of sines. This one will actually end up using something called the law of cosines. We'll probably touch on that. Build the suspense. Given two sides and one opposite angle, but here's the catch. The opposite side is the shorter side. Now, if I give you a picture, this isn't a problem. So if I give you this picture where you see that this is 38 degrees, and I tell you that this here is 18 inches, and maybe this over here, oh, let's call it like 13 inches. If I give you that picture, this isn't really a problem at all because I can tell what things have to be. But I'm just going to label this here A, B, C. So that makes this side little a, little b, and little c. If I just give you information like angle A is 38 degrees, side A is 13 inches, side B is 18 inches, and I don't give you that picture, there's actually a couple of different triangles you can make from this. We could make the one we just drew. Can anybody see the other one? This would still be 38 degrees. This would still be 18 inches. And this would still be 13 inches. See the issue there? I could fold this side in like that and I still make a triangle. I need to know whether side C or angle C is acute or obtuse. In the black triangle here, I drew it as acute. In the blue triangle, I drew it as obtuse. What if I tell you that it's obtuse? How do I find that angle? Well, I have my 13 over the sine of 38. There's my side, my opposite angle, right? I have the 18-inch side. It's going to go over the sine of C. I'm going to cross multiply and divide. Sine of 38 degrees times 18 divided by 13. I get 0.8525 basically. Yes, that means that C is going to be the inverse sine of that. Second sine, second answer. 58.48. Now let's look at our picture here. Is that angle 58.48 degrees? Say no. No. But remember, when we saw on our unit circle, we had a sine there of 0.8525. Sine of 0.8525 is like this, right? Is there another spot on that circle that has a sine of 0.8525? Right over here. How does that angle relate to this one? Well, this angle here is the same, isn't it? They have the same reference angle. That's saying this angle is that 58.48. So what's this angle have to be? It has to be the supplement. So the angle we're actually trying to find is 180 minus that 58.48, 121.52 degrees. So angle C there is 121.5. We will talk more about that case tomorrow. For now, I'm going to give you a new packet. And in this new packet, page 381, 1 through 17, is finding missing sides of triangles using law of sines.